in these series of lectures, I will start by revealing the secret for understanding the universe. This secret is probably known to you, but you hadn't realized the power of the method. The power of trying to understand, the passion for trying to understand, is a feature of human beings. And this was beautifully revealed in a letter written by a famous German mathematician on the 2nd of July in 1830. The mathematician was commenting on some remarks made by another famous mathematician called Fourier. And what he said was, Monsieur Fourier is of the opinion that the principal aim of mathematics is public utility and to explain the natural phenomenon of the world. But a philosopher like him must surely know that the sole end of science is to honor the human spirit. You see, unless you have this feature of trying to honor the human spirit, great innovations and great advances cannot be made. So that is our starting point. This urge to know and the tools which we need for them will now be revealed. The basic tool is the equality sign. This sign was first used in, I think, 1557 by someone in Wales, Welshman, and he chose the sign with great care. He said, what could be more useful than to have two lines which are identical? So the equality sign are two lines which are identical. That means that the sign has come from geometry. Now, once you have the equality sign, then the other huge advance made was when people introduced a symbol x for the unknown. This is a very, very, very powerful idea. So if you do not know something, you can still represent it. And this has become so standard and so familiar that we do not marvel at the power of the idea. Originally, the symbol x is associated with Descartes. When Descartes invented a certain form of geometry, which we will discuss later on, he had used the symbols x, y, z. But the printers in France told him that the letter z is used so much in France that perhaps would it make any difference if instead of using z, if they use x. And so he agreed. So that's how, by an accident of the French language, the letter x became the preferred symbol for something which is not known. So we have these two ideas, and then we come to the next step, which links what you are doing abstractly to the real world, and that is to introduce a system of units, a system of measurement. And what we find is that you need a unit of mass m, a unit of length L, this is mass, this is length, and you need t for time. So these three things, x and the equality, give you the power to tackle problems. For each step, generalizations and new ways of looking at the system of interest are necessary. So there is no algorithm for telling you how to do this, and this is a free creation of the human spirit. That's the way it goes. So let us now illustrate the power of equality in numbers and in geometry. First, we start with numbers. So for human beings to live at a sophisticated level, numbers are absolutely necessary. Once upon a time, the wealth of a person would depend on the number of cows he had or the number of camels that he had. So it was very important to count. So if I was richer than someone, it would mean I would have more cows or more camels. So counting was a very practical thing. At the same time, when the agricultural civilization emerged, then you had to own land, or the king owned the land and you cultivated the land, and very often you had to pay tax, and the tax was based on how much land you own. So measuring land was also a very important part of civilization, and that led to geometry. Now these two practical things have morphed and changed and have become beautiful constructions of the human spirit. So let us start with the numbers. So for numbers, I choose the number 2. Now there is a lovely story told by Richard Feynman. When Richard Feynman was young, his father took him to a park where there were many birds. His father knew many languages, and he said, this bird in Hebrew is called something. In Japanese, it's called something. In English, it's called something. In French, it is called something. He says, after you have learnt all of these things, you know nothing about the bird. So the same is true of numbers. If I say the number 2 is in English, if I say zwei in German, if I say dui in Bengali, if I say do in Hindi, you will know nothing about numbers. Then if I open a dictionary and if I look up the definition of a number, it will say that a number is a way of counting. It's a number 2, for example, follows 1, and if you add 1 to 2, it becomes 3, but if you know none of them, it doesn't help. So what happens for trying to understand something is you relate these abstract things to your daily life. When you begin to say, I have 2 eyes, I have 2 hands, and so on, you are on your way towards understanding. You are relating the thing, and then very soon you can use the numbers in a creative way. So start with the number 2, and I tell you that this number 2 can be written as 2. I have put an equality sign. So I have introduced equality in mathematics. I have said 2 is equal to 2, very little information. Then I write this as 1 plus 1. That's another relationship. Then I can write this as 3 minus 1 is equal to 4 minus 2 is equal to 5 minus 3 is equal to like this. So you see, suddenly what you find that in this one number, all the numbers are present. They are all hidden. And here I have not even put in fractions. So what you find is that infinity is lurking. This never stops. So the infinite number of numbers are all compressed and present in this one number. So I sometimes like to say that numbers have different faces. So I was once giving a talk to young people, and there was a girl sitting in front, a young girl, and I said, when you go to a party, do you wear this dress? And she said, no, no, I have a special dress for the party. And I told her, numbers are the same. They have different occasions, they dress up differently. And sometimes they may dress up just a simple 2, that is day-to-day life, right? And some special occasion, they might dress up as 3 minus 1 or 5 minus 3, depending on the circumstances. Now, it turns out that this very simple and rather trivial remark is not obvious to people who have difficulty with mathematics. Those who are good instantly know that this is the case, but those who have not been told this sometimes suffer. Let me give you an example of the advantage. Suppose I write 99 and I multiply it by 99. I want to do this multiplication, but then if I dress up 99 like this, then the calculation becomes much easier. So, this is what I mean by the power of thinking in a particular way, and once you have got that, you are on your road to inventing and creating new things, you see. And you might like to say that how many ways can you do this and so on, and each one of these has lurking in it different possibilities. Here I have written 2 in 2 different ways. If I give you a number n, an integer, positive integer, and I ask how many ways can I write this number n, you see. So, for example, in the case of say 3, I can write this as 3, I can write this as 2 plus 1, I can write this as 1 plus 1 plus 1. So, these are the ways, and I do not distinguish between 2 plus 1 and 1 plus 2, I treat them as the same. So, this problem is a very hard mathematics problem which was solved by Ramanujan. So, you see, right at the start of these discussions, we run into problems which are not trivial. The formula which Ramanujan discovered, which he proved with the help of Hardy, allowed him to give a very good estimate, you see, of the number of ways you can write one integer n arbitrary, right, in terms of other integers. Now, this great step of Ramanujan was experimental, he tested. You see, Hardy originally felt that if you give 10,000, if you can get an estimate to within a million, you are doing well. But Ramanujan felt that he would be able to get it to within 1. And so, for a particular number which he predicted that people knew, say up to 100 they knew, they had a table, there was a person called Major McMahon, he had made a table and he had stopped at some point. So, Ramanujan doubled that number possibly and wrote the answer. This is what you expect to get. Major McMahon went off and after 1 month's calculation, he verified that Ramanujan and Hardy's formula worked. So, this shows the power of imagination and abstract thinking and what is lurking in things which look very, very simple. Let me proceed with another example. This example is if I write 1 plus half squared and I do not stop, then this thing turns out to be 1 minus half, which is equal to 2. So, you see, again there is infinity lurking in this. If I stop at any stage, it is not equal to 2. So, I have to go all the way, I can never stop, right. And so, what you find is another example where 2 shows up in a different way. Then we also have, if I write any number n, I can write this as a k 2 to the power of k plus a k minus 1 2 2 to the power k minus 1 plus a0 2 to the power of 0. So, you can write use the number 2 any number, and this is again shows the power of equality. And so, you see it is not a sterile concept. Each time there is an act of creation, there is a creative way in which the equality is being used. And so, once we have written this, you all know that this is nothing but the binary system, and that is used in computers. So, anything can be written with zeros and ones, and so that is again a creative step. So, this is something I will come back to later, but for the moment you can see that equality is something which has lots of potential in it, and it is well worth reflecting on the richness of the concept. Let us now turn to equality in geometry. Now, for the moment we stick to Euclidean geometry, which is plain sheet of paper, and the Euclid's way of looking at it. So, in Euclidean geometry there is a notion of equality which is called congruence, right. So, the congruence will tell you that this triangle and this triangle are the same, they are congruent if the three sides are the same. It does not matter if I rotate, this could be in America, this could be in India, this could be in China, it does not matter where it is, they are the same. As long as certain things, either the three sides or two sides and included angle, or two angles and one side, and so on, they are list. Okay. So, once you have that, then you have another notion of equality. One of the things about the geometry of Euclid was that if you have two lines and they are parallel, they do not meet. Now, this thing has been analyzed very thoroughly by many people, and what you find from this is you have a notion of angle. So, this angle is the angle pi 180 degrees, right. And once you have this, by a few steps which you know, what you can prove from this is that if this is alpha, beta, gamma, then alpha plus beta plus gamma is equal to pi. And the way you prove this is you have this angle is the same as this angle is the same as this angle, and this angle is the same as this angle. Use these properties to derive this result. So, this is something to note very, very carefully. You have the idea of two lines not meeting, parallel lines, that is an abstract concept. Then you have a notion of angle, which is if you go from this to this, if you move like that, it is pi or 180 degrees. Those are statements about a straight line, but then you are making an experimental statement. You are saying that for any triangle, if you add these three angles, it has to be pi, and this follows from the fact that parallel lines do not meet. So, it is an experimental consequence which comes from the thing, you see. And so, again you see the notion of equality and the notion of the basic starting point of a system gives rise to things which are testable. Let me give you some example where these things are not like this, just to show you the richness of these ideas. as you know, or as you suspect, the earth is not a flat space. You know that the earth can be represented as a sphere. Okay? So, this geometry is not the geometry of the earth, it is an abstract geometry, which is valid because locally in this room the earth looks flat. So, what is this result for the earth? Okay? So, to do that, I draw this beautiful picture of a circle, almost perfect. You see, there is a story that the great artist Rubens once visited a friend, and the friend was not there, and Rubens just drew a circle and left. And the friend said, "This is a perfect circle. It must be Rubens must have come." So, you see, I'm not competing with Rubens, but this you understand, this is supposed to be not a two-dimensional circle, but the earth three-dimensional, right. So, on the earth, if I had a ball, you have earth, notion of the shortest distance being a line, straight line, tells you that 2 points, if they join by a great circle, that is then the straight line, right. So, let us take 3 great circles, one here like this, one there like this, and like this. This is so beautifully done, I have to pause and look at it for a little while, you see. But the beauty should not distract from what I am going to say, right. So, that is, this angle is supposed to be pi over 2, this angle is supposed to be pi over 2, this angle is supposed to be pi over 2. So, you have 3 angles of this spherical triangle, which from the picture, this fills 1/4 of the upper hemisphere. Okay? This is 1/4 of upper hemisphere, right. And now I will tell you a theorem, and the theorem says, forget this beautiful picture if you have to, for the moment set it aside. Then it says, if I have, this needs a separate line for it. If I have alpha plus beta plus gamma, this time for a spherical triangle, and if I subtract pi from this, this is equal to the area of the triangle by r squared, where this is for a sphere. Okay. R is the radius of the sphere, A is the area, so it will be this area. Okay. So, this thing in our example, right, we have pi over 2 plus pi over 2 plus pi over 2 minus pi. A hard calculation gives you the answer is pi over 2. Yes. So, this is where volunteers should say pi over 2, they should shout, and that is the way progress is made, by participation. So, this is equal to, what is the area? Area of a sphere is 4 pi r squared, and this is 1/8 of that, and this is over r squared, and this is equal to pi over 2. So, this is not a proof, but it makes the result reasonable. So, what this tells you is that when you are learning geometry, you should immediately ask, is this geometry the geometry on the earth? And then when you think about for 35 seconds or maybe 37 seconds, a prime number, then you immediately realize the earth is not a flat sheet of paper. It is not like that. So, then you might say, what is the analog of this result? Is there some analog of this result? And of course, mathematicians have studied this, and this is a lovely simple result, right, which has been established. It is much more general than the thing I've written down, but this is something which is relatively easy to remember. So this is what I mean by the power of trying to generalize and use the idea of equality. If you have a result in some branch, then you want to see, is there some analog result when you make a transition to a different system? And very often there is, and very often you can see that in this case, if r goes to infinity, then this right hand side goes to 0, and so you get alpha plus beta plus gamma is equal to pi. So it is consistent with the old result, but it's a generalization of it, right? So these things are useful, but another lurking very powerful idea, which I now have to point out, is that when we were doing with numbers, we were counting numbers, 1 or 2 or 3 or 4, like that. There were no units involved. But I said that you need x and you need MLT, mass, length, and time. So as soon as you go to geometry, you need a unit. Do you have 1 acre of land or 1 kata of land or 1 hectare of land? Makes a big difference. So you have to assign a unit, a length unit, right, an area unit. And so this is the next step which we discuss. Once you have, so we want a unit of length. Unit of area. You need these two, right? So unit of length, you take a point 0 and you mark and you say this is 1. And this could be 1 inch, it could be 1 meter, it could be 1 light year, right? It could be 1 micron, whatever. You've chosen a unit, right? But once you've chosen a unit, then when you add something to it, if you add 1 to this, then you get 2. So adding moves along the number line, and you can keep going. There's no there's no end point, and you go this way. And then you have subtraction, which goes in this way. So if I subtract 1 from this, I get this. If subtract, I get -1. Subtract, I get -2. And so the negative numbers are smaller than the positive things. And this is visual. You can see it in the visual thing. But here, there's some unit has been introduced. For the numbers, it's not essential, but the definiteness, I've chosen a 1 on the line, right? So now we come to the power of mixing. So we have mixed the number and geometry. This is a new idea. The number line appeared quite late, I think 1700 or 1800, quite late, right? But once it's introduced, it gives you a lovely result. The result is like this. Suppose I put 3 and suppose I put 4 like that, -3 minus, right? Suppose I want to look at 4 minus 2, right? 4 minus 2 from the picture is the distance between the number and this number. That's what this is. So this is the distance. Right? So if I want to subtract, I take the number and the one I subtract and I move, and this gives you this. Now look at 1 minus -1. 1 is here, -1 is here. What is the distance between them? It's 2 units. This implies that minus into minus is plus. Okay? So, the mixing is act of creation, and once you mix, there are insights, and this is an example of an insight, that suddenly something which you maybe have never thought about, maybe you couldn't go to sleep because you were too worried. I do not understand why whiness. It is not a rule, it is something which emerges as soon as you mix these two things, and there are many other. In fact, there was a International Congress of Mathematicians in Hyderabad a couple of years ago, and one of the great mathematicians of our time, Mumford, he gave a whole lecture on why minus into minus is plus, and it was quoting Euclid and all kinds of other people. Yes. The Euclid is a lovely example, which I will come back to. Okay. So, this tells you that we have got the unit of length, and immediately a consequence of that is this insight, a unit of area. So, what is the natural thing? What you take is a square. Since in geometry we know what is right angle, we take a square of unit, and this is a equal to 1. It could be centimeter squared or meter squared, etc. Right? It has units. Okay? So, we have this. Immediately there is a problem. How do I construct something which is area 2? So, for area 2, you need a square which is square root of 2, square root of 2. Right? How do I do that? Okay? There was a very, what should I say, a mathematician parent who tortured his little daughter by asking her to solve this problem. She couldn't. This is Pythagoras' theorem. This is what it is. So, let me explain by drawing a picture, and this is the way I believe Pythagoras discovered his theorem. It is always good to make a very strong positive statement, because then people feel he was wrong and they discover something on their own. So, my picture is Pythagoras was sitting and he was looking at the tiles on his floor. They were all one by one, like this, and then to his horror he found that these beautiful tiles had a crack here, a crack there, and a crack there. He was saying, I must replace them, and while he was thinking like a householder, suddenly his mathematical spirit came out, and the mathematical spirit says that this is half a square, this is half, this is half, this is half, this is half. So, this object has unit area 2. So, you have found an area 2 object without any measuring square root of 2, right. And then once he had got some delight in this new insight, right, then he also noticed that this was this and this added together. So, for a right angle triangle of size 1, he found that this area and this area also add up to 2. Now, for normal human beings they would stop there, but for a mathematician the next obvious question is this only true for this special triangle, or can one prove it in general? Okay. And this is what he proceeded to do. And what the one proof of this idea can be given like this, which some of you have seen. If you haven't seen this, you should have seen it. So, this proof, according to some people, it is Brahmagupta's proof, and he drew these pictures which I will explain, and he said, behold. And my good friend Divakaran, who told me Brahmagupta would never make a statement like that. He would never make this outrageous statement like behold. It must have been some disciple. Okay. So, here is the proof. This area is this whole thing, which is a squared, this area, plus b squared plus 1, 2, 3 plus 4 triangles. Yes, that is this area. Now, what I have done is I have kept here b, but I put a here, b there, a there, b there, a there, b there. So, this area is the same, right. All I have done is I have flipped the a and b, right. The area of this is the same. The length is a plus b, the whole area of this is a plus b squared, right. So, but this time you have these 4 triangles plus this is c plus c squared. Now, to prove this is a right angle is quite easy. You just show this is right angle, this plus this must be right angle, the alpha, beta, and so this is beta alpha, and so alpha plus beta is 90, so this is 90, right. So, these technical details are very important, but I think conceptually what you have is an astonishing result that a squared plus b squared is equal to c squared, where you have a right angle triangle, any arbitrary a and b, and you have Pythagoras' theorem, right. So, here this act of imagination. Imagination was, although you are dealing with triangles, the bottom line is you really in geometry are dealing with area. And once you have that hit in your head, it is an area, then you say, why don't I think in terms of area? Once you have done that, you get this very lovely result. So, I think what we have done is to sketch the power of the equality sign, and I have tried to give some examples where this particular power is manifest. What I have not said in this particular talk is the unknown x. I will come back to that in my next talk.